Hello, AP Physics. We are going to start our next chapter, chapter 23. It's the final chapter in electrostatics, and it is the one we'll take the most time with. It is by far the most abstract. I kicked around throwing it out, in fact, because I can't picture teaching it to you from afar. But it's something that I would have been ever so grateful to have had some exposure to when I took college physics, so I decided to keep it, and we'll see if you can make some sense of it. The math is not hard. Again, it's just the abstract idea. It's very hard to picture. It's not quite as intuitive as anything else we've studied, and it's hard to see the connection to circuits, which is where we're going, because you really don't get into it until later in electricity. I don't think we'll get into it this quarter. So anyways, this huge abstract concept that I thought about not doing is called Gauss's law. And so we essentially have two major concepts in this chapter. One is a new concept called electric flux, and then the second is Gauss's law. So Gauss's law uses flux in his mathematics. So today we're going to talk about flux. And so I'll define it formally in a minute, but flux is field lines piercing a surface, okay? So we've talked about electric field, and we know that field lines, when we draw them, they point out from positive charges and into negative charges. And so, sorry, Asher's on the attack. And so in this chapter, what we're going to do is have all kinds of imaginary surfaces that will enclose a charge, and we use flux to kind of figure something out about the charge. So, for instance, because this is sort of strange, let's say that I have three different charges. One will be 2Q is positive, one will be Q, also positive, and one will be negative Q, so clearly negative. So if I were going to draw field lines for these, I'm going to draw twice as many, because it's hard for me to control color here. Twice as many field lines going out of the 2Q charge as I do the 1Q charge. I don't know if I'm doing exactly twice, guys, but you get the idea. So I have more lines coming out of this charge than I do out of this charge, and then here, because it's negative, I'm going to have lines going into the charge. Okay, so if I drew my field lines, and let's just even make this a little easier picture. Negative, positive. This is like 2 plus, twice the positive. Okay, so if I were going to look at the electric field and try to diagram it so I could visualize it from 3 different charges, I would see field lines coming out from my positives and going into, that might be hard to see because I'm noticing my lighting's off, going into my negative, changing my lights. And I'm going to see more field lines going out from the 2Q and fewer out from the single Qs to indicate that I would have a stronger field here, right? So what we do, what this Gauss does is, it's very, again, very hypothetical and abstract. Says, what if we draw a surface or a shape, right? It's not going to be like a solid surface. They call it Gaussian surfaces, but it's just, what if I draw a shape to enclose these charges? So in this, just because look at the shapes I have drawn, circle would be my good choice here. So what if I have a circle? I'm going to do it in blue dotted lines, so if you can see it, around each one of these. And what if, so you kind of imagine them like wrapping paper, these blue lines. I always use the metaphor of wrapping paper with Gauss. What if I did not know what was inside here? What if I could only see what was piercing, so the field lines that were piercing the blue circle? So again, those field lines piercing the blue circle, that's what we're going to call, in a moment, flux, right? So flux is our field lines piercing an area or surface. So if I only saw the blue and I didn't see what was inside, I see a field lines piercing out field lines piercing out, field lines piercing in, right? So I can see them going into the blue, out of the blue, out of the blue. So even if I have no idea what's inside, I know that there must be a positive charge inside these two because I see these field lines piercing out. And I know, yeah, you have thoughts about that, buddy? I know that there must be a negative charge inside here because I have field lines piercing in. Also, if I had no idea what was going on inside, I see a lot more field lines piercing out of this Gaussian surface, out of this blue circle, than there are piercing out of this blue circle. Sorry, Asher's got things to say. So that means that whatever's inside here has to have a bigger charge than what's inside here because it's producing more field lines that are piercing out. So that's kind of the conceptual idea. Again, I'm not quantifying it yet. I'm just using lines to tell me. But that's what Gauss does. He comes up with a law that we'll talk about later in the week. He comes up with a law that relates this flux, these field lines piercing a surface, to what is enclosed inside the surface. So you essentially have two options with Gauss in this chapter. We're either going to know what's inside and be able to find the electric field on a surface. So this is much more complex than like our KQ over R squared stuff we were doing last week. Or we can know this electric field. They can give me the electric field or the flux, and then I can figure out what's inside. So he's relating those two quantities. So again, in order to use his law, we need to kind of know or quantify this flux. So by definition, I'm just making sure I follow the PowerPoint, sorry. So we're coming close. Say hi, Ash. By definition, electric flux is defined as the amount of electric field piercing a surface. So there's a whole calculus setup. I'll kind of write it that way. We never really do calculus when we do Gauss the first time around. Now, some of you, I know right now, I don't think any of you are seriously considering, I might be wrong, electrical engineering or a physics degree. If you were going to study either one of those two things, you will be taking multiple years of E&M. But most of you will probably just take like this level, what we're doing now, course next year or the year after. And so when you do Gauss, again, you're going to pretend like you're doing calculus. We'll write it with calculus, as I will now. But we're really just multiplying numbers. We're never going to actually do calculus. So I'll write it with these strange symbols now. You'll see them in the PowerPoint. But really, flux, this is our symbol for flux, is equal to electric field, so the value for the electric field, times the area that it is piercing. So when we're actually solving problems, we're just going to take E and multiply it by A. Okay, so I'll try and be like official and use the calculus, but we're really not. We're multiplying two numbers. The trick here is these two numbers are both vectors. And so we're doing something called a dot product of a vector. So for the record, the dot product, oh my goodness, the dot product is the product of the two times the cosine of the angle between them. We are going to hopefully be working with the field lines actually piercing, so at a 0 or 180 degree angle, the angle between them. So the cosine of 0 is 1, cosine of 180 is -1, and we shouldn't really see other, we shouldn't really see other angles involved. So again, for us, just math-wise, I'm not going to be, oh goodness, I'm not going to be writing down cosines because it's not something we'll be using. What that corresponds to, that 1 or -1, is if the field lines go out. So if they go out of the surface, then we say that the flux, that's like the 0 degree basically. We say that the flux is positive. Oh my goodness, I gotta lose the earrings. My ear's getting pulled out. And if the field lines go into the surface, then we say that the flux is negative, which corresponds really well with field lines going out from positive charge and into negative charge. So it's not really anything different from what you have seen before. Okay, so calculus-wise, you know, you see, if you have a surface, there's like a sheet that they're using, and you have a field line piercing here. We call this a little area, right? And this electric field is piercing this area. And so they say the like one little flux or change in flux is equal to the electric field in that area. And if I wanted to know what's happening across this whole sheet of charge, well, I would integrate. And so the total flux would be the integral of the electric field with respect to area. So this is the way you see it. I did not do a real derivation there. I'm just kind of jumping guns there. But because if you're in my calculus class, you haven't seen this sort of thing yet. That's a bit of a Riemann sum. If you're in AP calculus, you know what I'm saying. If you're not in calculus, you have no clue. And that's just fine, because this is all we're actually going to use. But you see this symbol in the book a lot for it. Okay. So what we'll do when we're finding electric flux is we'll take our, no, you have things to say. We'll take our electric field and we'll multiply it by the area that electric field is piercing. If the field lines are piercing out of the area, we say it's a positive flux. If the field lines are piercing in, we say it's a negative flux. If we have a situation, we're going to look at it in a moment with a cylinder. I'm going to do 2 problems on the next video. If we have a situation where the field lines are running parallel, then we say there's no flux. So the field lines must be piercing a surface for there to be flux. Again, at this point, and even in the next one when I do the problems, if you're saying, I still just don't really quite get what flux is, it's a strange thing. Just bear with me. Take it through as long as you're mathematically following me, we'll keep coming back to this concept throughout the chapter.